Hopefully, yeah, there we go, we're recording. Okay, so parametrization. This is really, I know it's a big word, and some students were like, well, how is this different from what we have been doing? Well, what we were doing is we were taking parametric equations and turning them into Cartesian equations, right? We were eliminating the parameter. With this particular lesson, to parametrize something means to go the other way, to turn a Cartesian equation into a parametric equation. So that's what we're doing today, is we're learning how to go the other way, turn a Cartesian equation into a parametric equation instead of eliminating the parameter. So we're going to really basically be working with two different types for the most part on this lesson. One is lines. We're going to turn lines or line segments into parametric equations. And the other is circles or ellipses. We're going to turn circles or ellipses into parametric equations. So that's our goal for today. So what do we do? All right, so let's look. If we want to turn a line into parametric equations, there's a couple of different steps. We would need 2 points on the line, and point A and point B. And we're going to write the parametric equations going from A to B. We're just always going to go from the first point to the second point. And what we would do is our step 1, we would find the vector from A to B. So we know how to write vectors. That shouldn't be a big problem. We're just going to take the 2 points and we're going to write a vector. The second step, now it sounds a little weird until we do this, we're going to add a scalar multiple of the vector to point A. Basically, it's similar to finding a point between this, like finding a point between a segment. So that probably doesn't make any sense yet. I do have an example that we're going to do that with, so that'll make more sense. If we want to turn a line segment into parametric equations, we actually do the exact same thing as we do with lines, but we have an additional step. We want to restrict the interval from 0 to 1. Now, because of the nature of the way that we turn a line into a parametric equation, it's always going to be from 0 to 1, t from 0 to 1. And I'll show you, when we do this, I'll show you why. Why is it going to be from 0 to 1? Always, and it will be. So that's how we would do lines. Okay, that's the steps. For a circle, if you recall, this is our standard equation of the circle where h and k are our center of our circle and r is the radius. In order to turn a Cartesian equation of a circle into parametrics, we're going to have to use this concept. And basically, we're just going backwards from what we did before. Hopefully, it will make sense to you when we get to that, but it's just going backwards from what we did previously. So let's start out with lines. Those are a little bit basic. So we're going to do a line segment. That's more restrictive than a line. That's where we have to add our time restriction to it. So what do? Well, first of all, let's go back to these instructions. We're going to find the vector from A to B. So here's my first point A, my second point B. I need the vector AB. So if you recall writing the vector, it's end minus the beginning, right? The end x value minus the beginning x value, the end y value minus the beginning y value. So 3 minus a negative 2 would give me 5, and 4 minus 6 would give me a negative 2. So there's my vector. I've done step 1. And step 2 is writing it like a vector equation of a line, which we kind of looked at briefly last week. We kind of looked at that briefly. It was, if you recall, x comma y equals. Remember that? We had that in the front. And then we had, we're going to always take the first point and put it here. Always. That's my point. We're going to take my first. And the reason it's the first point, always, it has to do with the timing from 0 to 1. That's what makes the timing 0 to 1, is always we take the first point and we add to it that t with the vector 5, negative 2. Okay, so this is a point. Oh, those are bad parentheses. That's a point. So we are going to take the first spots. Hopefully you remember. I'm just going to remind you. So the x is going to be equal to negative 2 plus 5t. Remember how we turned that into a vector, or from a vector to a parametric? So my parametric equation is going to be x equals negative 2 plus 5t, and y equals 6 minus 2t. And we're going to restrict it because it's a segment, so it stops. It doesn't, go for infinity. It stops. And our restriction is always 0 to 1. Now let me explain why. Let's go through and I'll demonstrate why it's from 0 to 1. If you chose another point on the segment besides the beginning point, you would have a different restriction for time. And that would just cause lots of more work. So why would we want to do that? We're just going to use the first point. Because what happens? What happens if I put a 0 in this parametric equation? So if I put a 0 in for t, that would go to 0 and that would go to 0, and I'd be left with negative 2, 6. See how that's the first point? At time equals 0, my first point is negative 2, 6. That's what I want. If I were to put a 1, this last one in for t, I get negative 2 plus 5 is 3. Well, that shouldn't be a surprise. That's my x coordinate of my last point. And I put a 1 in the y section, and I get 6 minus 2 is 4. So that's why it's always 0 to 1, because of the way that we created this set of parametric equations, or this parametric equation, is we cause the first point to be, our addition right here to our vector. Okay, hopefully that makes sense. That's why it's always 0 to 1. It's because of the way that we wrote the vector, which in turn created the way that we wrote the parametric equation. Okay? So the next one, they don't give us any points. It's a vertical line at x equals 2. So let's just think about the Cartesian equation for a minute. We have x equals 2. We've got a vertical line. We really need 2 points. We need 2 points on a line to be able to write a vector, and then therefore write the parametric. So I chose 2 points. You would need to choose 2 points. Every point is going to have an x coordinate of 2, right? Every point will, because that's, the x value. So I chose 2, 0 and 2, 1. I would encourage you to choose easy points like that. Do I have to choose 2, 0 and 2, 1? No. I could choose 2, negative a million if I wanted, or, if I wanted to, but why? Right, we're just going to make it simple, 2, 0, 2, 1. And to take, this is going to be my point A, and that's my point B. Okay, so now I have points A and B. I'm going to, just like I did above, I'm going to write my vector. Vector AB is going to be end minus beginning, right? So 2 minus 2 would be 0. And 1 minus 0 is 1. So there's my vector. Let's say I had picked a different point. My x coordinate, or my horizontal component of my vector, is always going to be 0, no matter what point I pick, right? Don't they all have they all have x values of 2? So that's always going to be 0. The only thing that would be different if I picked a different point would be this component. And, that I have a unit vector. It's just easier to work with unit vectors. That's why I picked the 1. So I would encourage you to do the same. Alright, so that's my vector. My first point is 2, so 2, 0. So let's write our vector. xy equals, my first point is 2, 0, plus t times my vector. Alright, so now let's write the parametric equations from that. So x equals 2 plus 0 times t, which is just 2, and y equals 0 plus t, which would just be t. So that's my set of parametric equations for my vertical line at x equals 2. Again, if I chose a different point, the only thing that would be different here is this second equation would be different. The y equation would be different. This x equation is going to be the same. It's going to be 2. But if I chose a different point, this would be different, which is fine. It's just a different way to represent that line because it's infinite, right? It's an infinite line. So I don't have any restrictions, and I wrote it with those 2 points that are 1 unit apart. Okay, we okay with that? Okay, so that's how we parameterize lines. So let's go to the next page, and let's look at circles. Okay, so the standard, this is x squared plus y squared is 36 in standard form. Our radius is 6, and our center is at the origin. So what they're having us do is just like a little bit of a lesson in translations and how that affects equations. Hopefully we remember. So if we translate it 3 to the right and 5 up, basically what that's going to do, it's going to change that x to x minus 3, because I went 3 to the right. Remember, it's always opposite, which is all I know troubling. That's just the way it is. And then 5 up would be y minus 5 squared. So that's our new equation. Now, normally, I know this was troubling to some students earlier, the y coordinates usually are like just exactly what you think. If you're going up, it's plus. But this is trapped inside there with the y, so it behaves just like I'm talking about translations. This behaves just like the x translation. If this says minus y minus 5, that means I'm going up 5. If this is x minus 3, that means I'm going right 3. Hopefully we recall that from our transformation days. Alright, so there we go. So what we're going to do is we're actually going to work backwards. Maybe, hopefully you kind of remember how we went from a parametric equation of a circle or ellipse to a Cartesian equation. But as we go backwards, maybe your memory will come back, right? So maybe you already remember. We were equal to 1. So I would divide each by both sides by 36. So I'd have x minus 3 squared over 36 plus y minus 5 squared over 36 equals 1. Now I'm going to turn that 1 into cosine squared plus sine squared. Now the variable that I want to use with the cosine and sine is a t. So I'm going to turn that into cosine squared t plus sine squared t. And I'm going to match the pieces up. Now this is kind of important. Students were having a hard time with this earlier. The counterclockwise versus clockwise. The way that I match these up determines which way I'm going to rotate. And we did talk about this briefly when we did this lesson, but you may not remember. If I match up the x with the cosine, that's normal, right? That's normal. That means I'm going counterclockwise, because that's normal for us, is counterclockwise. We go from the x-axis counterclockwise. Right, so if it tells me that I want to go counterclockwise, I'm going to match up the x and the cosine. If it doesn't tell me, then I'm going to make it go normal, counterclockwise. Let's say we want to go clockwise, because there actually is one on your daily work which asks you to go clockwise. Then what we would do is we would do the opposite thing. We would match up the x with the sine, because x doesn't go with sine, right? And then we would match up the y with the cosine. And that would cause the graph to go clockwise, to move clockwise. Okay? So we just want it regular, so we're going counterclockwise. So we're going to match up, we're going to say x minus 3 squared over 36 equals cosine squared t, and y minus 5 squared over 36 equals sine squared t. Again, if we wanted it to go clockwise, we would have to reverse that. So now we're going to square root both sides, and we only care about the positive root. So I have x minus 3 over 6 equals cosine t, and y minus 5 over 6 equals sine t. And now we solve for x and y. See how we are moving backwards from what we did previously? Now we're going to solve for x. So I'm going to multiply both sides by 6, and then I'm going to move the 3 over. So I get x equals 3 plus 6 cosine t. And I'm going to move on the y equation. I'm going to multiply both sides by 6 and then move the 5 over. So y is going to be 5 plus 6 sine t. Okay? So if I was going clockwise, this y would not have a sign with it, right? The y would have the cosine with it. And this x would not have the cosine with it. The x would have the sine with it if I was going clockwise. Are we clear about that? Is everybody okay? Okay. Now, this little circle, if I don't put a restriction on it, the poor little guy is going to be going in a circle forever. Over and over and over again. Let's help the little guy out, right? Let's give him a restriction. We want t to be between 0 and 2 pi so that he only does one circle instead of like an infinite number of circles. So let's go ahead and write, I'll just rewrite the equation. So x equals 3 plus 6 cosine t and y equals 5 plus 6 sine t. And we're going to restrict t between 0 and 2 pi. And there's our parametric equations. Okay? The last type problem we're going to do today on today's notes has to do with parametrizing something other than a line or, a circle. And that is, we're going to look at a quadratic. And we're going to be given what they want us to use. And basically it's called the parameter. Use the parameter that's given to write the parametric equations representing that Cartesian equation. So we're going to work with two parameters. We're going to do the first one where we're going to make t equals x, and the second one is a bit more complex. We're going to make t equal 4x plus 1. And in changing the parameter, we're also going to look at and measure the speed and orientation of the way that it's going. Okay? In order to do that, I'm going to need the distance traveled to be the same for both. So just kind of keep that in mind. I'm going to set the distance traveled with A, and then I'm going to force the distance traveled to be the same with B. You're like, what are you talking about? It's okay. We will get there. So first, on this one, we're going to do the simple one first. I'm going to replace the x with a t. This is the equation that I'm going to turn into a parametric equation. And I'm going to replace the x with a t. So I have y equals t squared minus 4. And then we already know what x equals. They told us x was t. That's my set of parametric equations. Okay, the first one is pretty easy. Now, this is a parabola, x squared minus 4. We know what it looks like. It's down 4 spaces, right? What I would like to do, and on a quiz or a test, I would tell you how much to graph. Okay, so just don't worry about the ambiguous part of this. I would tell you. We're going to compare these, we're going to basically graph from a this x value as -3 to an x value of 3. That's what we're going to do, an x value of -3. So we know in this particular equation, if x was 3 or -3, we would be up at 5. So we're going to do this when t is -3. We're at 5. And if that's kind of freaking you out, you're like, how do you know that? You could do a t-chart like this, and you put a -3 in. So you'd plug that -3 into your equation. T would be -3, and y would be 5. So if we want to know what happens when t is -2, x would be -2, and y would be 0. So we're headed that way. If we want to know, let's go to 0. When t is 0, x is 0, and y is -4. So that's when t equals 0. I'm just putting some of the times on my graph to kind of let's give us an idea of what's happening. Okay, so let's say I want to know what happens when t is a positive 2. That means x is a positive 2 and y is 0. So that puts us up here. That's for t equals 2. And then we would finish out. This would be t equals 3. Okay, is everybody okay with that? So that's the distance that we're going to travel. We're going to travel that exact, part of the parabola. The time, and you would be told what the time is. Let's say that time is in seconds. So for this rendition, with my parameter being x equals t, or t equals x, the time that it took me to travel this distance was 6 seconds. So say we have a particle that's moving, it takes 6 seconds using that parameter to go that distance. Okay? So now we're going to do the more complex one. This one has t something other than just x. It's 4x plus 1. So what I need to do to turn this into a parametric is I'm going to have to solve for x. I mean, the first one, x, I was already solved for x. It was kind of nice. The second one is not that easy. So we're going to solve. So we'd have t minus 1 equals 4x. So x is going to be 1/4 t minus 1. Okay, so that's my x. Actually, that's my x equation, right, in my parametric equation. I need my y equation. So I'm going to have to replace the x in this equation with this, 1/4 t minus 1 thing. So let's do that. So y equals 1/4 times t minus 1 squared minus 4. So I just replace the x in my parabola equation with that representation for x, the 1/4 t minus 1. And now I'm going to, do algebra. So 1/4 squared is 1/16. T minus 1 squared is t squared minus 2t plus 1. Okay, then I'm going to clean it all up, distribute, combine like terms, all that super fun stuff. And I'm left with y equals 1/16 t squared minus 1/8 t minus 63/16. Alright, so my equations are x equals 1/4 t minus 1 and y equals 1/16 t squared minus 1/8 t minus 63/16. With a different parameter, we get different equations. It's still going to create the same graph. Strangely enough, it's still going to create the same graph, this exact same one. So what I want is, I want to know when x is -3, see that that's my starting point, when x is -3, what would I have to make t in this rendition for x to be -3? Well, I would just need to use this little equation, -3 equals 1/4 t minus 1, and see. I have to solve for t. Multiply both sides by 4. -12 equals t minus 1. Add the 1 over. I get what? -11. So right here, t is -11. Okay? So what I'm really interested in is the beginning and the ending. I want to know, because I'm interested in the speed. I know that it's going to go, that's what it's going to do. And if you don't trust it, you can find all those values. I promise you it will give you that exact same graph. But I really need to know where I start and where I stop because I need to see how long it took. We're looking at speed. Orientation, we have figured out the orientation is just the direction it's going. So if I'm not sure, let's just say what if x were 0? 0 equals 1/4 t minus 1. Multiply both sides by 4. 0 equals t minus 1. T is 1. So when x is 0, t is 1. But I really want to know what is t when x is 3. Right? That's going to tell me how long this took. So when x is 3, 3 equals 1/4 t minus 1. Multiply both sides by 4. 12 equals t minus 1. So t equals, what, 13? Okay, so we end at t equals 13. So although we make the same graph with this set of parametric equations, we travel the graph in a different speed, completely different, because the parameters were different. So in this particular configuration, it actually took us 24 seconds to make the same path, the same distance as the original one did. So this would take 24 seconds. And how do I know it takes 24 seconds? Well, I started at negative 11 seconds. That's where I started. And I ended at a positive 13 seconds. So that would take me in time, not negative versus positive, but just in time, that would take me 24 seconds. So that parameterization caused the particle to move slower. Do you think you could find a parametrization that caused it to move even slower than this? I'm sure we could. There's actually an infinite different ways that we could parametrize this particular or any Cartesian equation. Okay, how are we? Are we okay?